Okay, so welcome to the first episode of this Bohemian Cafe. This is the second take because the first time we had a little technical issue, and I'm very happy to introduce this new series of talk. And today we'll have Michael Makkai with notions of identity for higher and for higher dimensional categories. Professor Makkai, you can share your screen whenever you feel like, and you can start your presentation. So while you share your screen, I would like to thank everybody that has joined today and that is giving us the second opportunity of attending this talk. Please, Professor Makkai, whenever you want.
Okay, so greetings. This kind of global reach, a very new experience, of course, for me. One is inspired to quote Schiller, diesen Kuss der ganzen Welt. But on the other hand, probably it is a very smooth and simple thing. Let me start by saying that there are four pieces of four sets of slides, as a matter of fact, and probably you will profit from having them in front of you from time to time. I'm going to use them, but only sparingly, actually, because of course I don't have time to go through all of them in all detail. All right. Now, folds, first order logic, the dependent sorts, is intended to be a framework for a formalization and the meta theory of that formalization of structuralist mathematics. Okay, so I use this italics here in the sense that maybe the term requires some kind of explanation, and hopefully what follows gives a bit of an explanation. Ordinary first order logic, FOL, provides the language for axiomatic set theory, the accepted basis for pure mathematics nowadays. On the other hand, FOL as a model theory, their isomorphism of models is the operative identity concept in the model theory of even extensions of first order logic, infinitary or higher order. Two isomorphic structures cannot be distinguished by model theoretic properties. The two sides of FOL, namely the foundational side and the model theoretic side, come together in axiomatic set theory, where the interest is in models, sometimes in models in toposes other than the category of sets, for instance, Boolean valued models, that is, models of various combinations of set theoretic axioms. Folds is intended to serve in both roles, the foundational and the model theoretical. Folds is a specialized first order logic. Every folds formula is equivalent sort of automatically to a multi-sorted first order formula, but not conversely. Folds has a semantics that is simply inherited from first order logic. As a result, the general model theoretic facts of compactness and Löwenheim-Skolem theorems, to give examples, remain automatically true for folds. Here I make a remark which is not in the text written down, that completeness for folds is a bit more delicate and important thing here. And of course, it is not a purely model theoretic thing either. The difference to ordinary first order logic in folds is that in folds we require invariance of all defined predicates under the new notion of false equivalence. False equivalence is a parameterized family of so-called L equivalences, one for each false signature L. In each case of a false signature L, it is meaningful to talk also about isomorphism of L structures. But there are more L equivalences than isomorphisms. And invariance under L equivalence is thus a more stringent requirement than isomorphism invariance. Bourbaki not only practiced structuralist mathematics, that I'm now going to abbreviate as SM, but also gave a prescriptive definition for it. SM, first of all, is to be based on a formal axiomatic set theory. The essential part of the prescription is that SM is based on a system of species of structures, with each species S given by an explicit set theoretic definition. It is required, I repeat, it is required that the definition of S be such that it is possible to transfer a structure by a bijection F of the underlying set A of M to another set B, producing a uniquely defined new structure N of species S, this underlying set B, which is isomorphic to M, by the isomorphism mapping F. Now, there are two examples here which actually become quite relevant in the concrete example of the signature later, which I'm going to skip. Further, only those properties of structures of a given species are allowed in the theory, which are invariant under the isomorphism notion of the species S. As a result, one cannot, in polite company, talk about identity, sameness of two free living structures in a more stringent sense than the isomorphism of them by force of the requirement, Leibniz's rule, that structures M and N are identical if and only if they share all meaningful properties, since now the meaningful ones are only the isomorphism invariant ones. I put in the free living proviso above, since, for instance, the equality in the usual sense of two subgroups of a given group remains, of course, an allowable predicate. But a subgroup of a group is not just a group. It is equipped with the additional structure of its embedding in the container group. Bourbaki's prescriptions had been instinctively followed by most of the practice of pure mathematics starting in the early 20th century, well before Bourbaki's definition of structure, similarly to axiomatic set theory before the latter's explicit statement. But since in axiomatic set theory, says EFC, a randomly chosen property of a structure, say a group, example, the natural number 5 is an element of the group, is not isomorphism invariant. And constructions such as the union or intersection of two sets are not isomorphism invariant. Bourbaki's prescription is far from empty. False provides an adequate restatement, in fact, at least two such restatements of axiomatic set theory in which all properties of structures are automatically invariant under isomorphism. One such will be our second example, abstract set theory in the false language of the signature L sub abstract set. The other one is axiomatic restatement of Bill Lavier's first order theory of the category of sets combined with Lavier's topos theory in the false language of categories, the latter being our first example. With the advent of category theory, Bourbaki's structuralism became too narrow. To begin with, for categories, isomorphism turned out to be too restrictive. For most purposes, when categories C and D are equivalent, in the usual technical sense that is weaker than isomorphism, we may regard them to be identical for most purposes. If C and D are equivalent categories, then all isomorphism invariant constructions in C, in the sense of isomorphism in C, in the category theoretical sense, can be transferred to D. And isomorphism invariant properties of those constructions will be preserved by the transfer construction. An example of such a construction, one of a huge number of categorical construction, is the binary product of two objects X and Y. As we will see, the capability of transferring content from one L structure C to another L structure D is at the heart of the general notion of L equivalence. Here, L structure is a species of structures taken as basic in false, depending on a so-called false signature L. As to the example of categories, they will be regarded or recoded as L structures for a specific false signature L sub cat, treated as our first example. Let me skip the rest of this introduction and go to the general just a moment, yes. The general part of the story. Let me just go up here. So I'm going to give definitions, but I'm going to skip some detail actually. And I will sometimes jump to examples and come back. So first, we are giving some conditions that make a category L into an L signature. Now, I skip that and definition and I go to the example. So let me do this here. It is an example for an L signature. So it shows, the picture shows all the non-identity arrows of this category, which has 5 objects, okay? Of course, O is going to stand for the word object, and A arrow, and I identity, E for equivalent, and T is triangle. And then, of course, there are these relations between the arrows as I show here. And now let me jump back to the general definition. Okay, just let me see. Now, given that I have this definition, let me go to the definition of the main concept. In fact, maybe I should say that there are 2 concepts here, 2 fundamental concepts. One is the syntax, and the other is this new notion of L equivalence. So the point about it is that, the first point about it is that it relies on an extremely simple and in fact well-known idea, which is what I call the fiber by surjective map. Now, this is a natural transformation. P is an L structure, and therefore it is just a functor from L, which is a category 2 set, and M similarly. So L is just a natural transformation. And fiber by surjective is what you would call a trivial fibration. And let me keep it that at the moment, okay? The point is that in this very rudimentary context, I can define this concept and it will turn out to be the basic thing. Okay, now, here I make an obvious remark, which I'm also skipping. And now I am coming to maybe the main definition. Okay, so the L equivalence between two L structures, M and N. So it's a notation that P is an L equivalence between M and N. Now, what is such a thing? It's a span. It's a span of two Fs fiber-wise surjective maps, as the picture shows. Okay, you say that the M and N are in the L equivalence relation if there is such a equivalence object which provides this relation. Now, it is absolutely the most important thing for everything that happens from now on is that we not only have L equivalences between structures, but we have such things between augmented structures. Now, what is an augmented structure? You take an X, which is just another functor from L to Z. By the way, this is quite a remarkable thing that these functors play two very different roles. X really is a diagram type, or also a context of variables. If we make the connection with the usual linear syntax. But now it is just another functor, and for the sake of intuition, let's require that X is finite. For actually the definitions that follow, this is not even important. Now suppose that there are two X objects, one in M and another one in N. For instance, the simplest example would be that X is the terminal object in the category of functors from L to Z, and alpha is simply if M stands for a category, an object in M, and beta is another object in N. And I'm now trying to say when these two objects, the alpha and the beta, are equivalent, okay, or carried to each other by an equivalence, what this should mean. And it is this very simple thing. So P is such a carrier, such an equivalence, if, to begin with, P itself is an equivalence in the original sense of between the two structures M and N. But then there should exist a mediator, a gamma from X to P, such that, of course, gamma will project down to alpha on the left and beta on the right. Okay, so this is the basic definition now. Not equivalence, not only of structures, but augmented structures. Now, here is, it's quite easy to show that this is as a relation, it's an equivalence relation, and this hides the fact that you can compose equivalence objects. Of course, and the composition is quite familiar. It is the composition of spans using pullback. Now, here is a basic argument, so to speak, actually a fact, which is at the heart of many things that we are going to see. This is equivalence transfer. And the word transfer is is a reference to the use of the word by Bourbaki. Suppose that now I have, again, this alpha and beta, two similar diagrams in these two structures, and then suppose that they are actually equivalent. And now suppose that we extend the diagram type X by a monomorphism to a bigger one, say Y. And suppose that, in fact, I have also extended one of the diagrams, namely alpha, to alpha bar, to one to become of type Y. Now the claim is then there is also an extension of beta to a similar okay, so an extension beta bar of beta to a Y-type diagram, so that now the resulting extended augmented structures are equivalent. In fact, not only that, but in fact, the carrier equivalence is the same as it was before. Now, in the next page, there is a proof of that, very simple one, and the only which I'm skipping. So the point is to see that this is exactly where I use what fiber-wise surjective means, of course. Now, equivalence transfer is used to show the soundness of L equivalence with respect to false properties of augmented structures. Now, here I use a model theoretic statement formulation. So phi here is a false formula. I have not made any attempt as yet to actually define what that is. But maybe I should say that this is where the word dependent types appear, and dependent sorts actually in my language, but they are exactly the same kind of thing as, for instance, in Martin-Löf type theory. The whole point is that there are no, it's very simple. So this is why I use the word sort instead of type, because there are no type construction at all. There is only quantification over type variables, and there is no manipulation of types anymore than that. Okay. Now let me just go back to this. Therefore, the soundness of L equivalence, of course, is that it fits the false syntax in this sense, that if I have that two augmented structures are L equivalent, and one satisfies, now this is the model theoretic notation, M satisfies phi when I interpret the variables in X by the assignment alpha, okay, so M satisfies phi at alpha for X, then the analogous statement is true for N and beta. Here I just make a small remark here that I use this extension of a diagram type X, Y, and it was required to be a monomorphism. Now, in logic terms, what is going to happen is that I am willing and I am allowed to quantify over this. Now, when I say this, you should think of a Laverian hyper doctrine. And of course, these quantifiers are up in the total category of this of the vibration. But all right, now here we come to an important and somewhat unexpected element here. Now here once again, L is a false signature and fixate, and M is a fixed L structure. Now, we are going to look at self-equivalences of M as it is here, okay? Now, I say that this extends the identity in the obvious sense, where basically what this means that, so here is the diagram, okay, which is the definition. What this means is that the L equivalence makes everything equivalent to itself, okay? Now suppose that I have such a thing, and now I have two elements, alpha and beta, of the same type, but in the very same structure M. Now I want to say, just to have a word for this notion, that they are intrinsically equivalent if there exists a P extending the identity, which carries alpha into beta, okay? Now, this is that I'm going to use as a notation. Now, let me sort of motivate, first of all, in this case. Just without having the extending the identity property of this carrier equivalence, once I know that alpha and beta in the very same structure are so equivalent, then I know that they will satisfy the same properties. But I want more. I want that they are actually identical in the internal sense of that creature, this M, this L structure, which is now considered as a kind of universe. Well, for instance, when in the case of categories, M is basically just a category. And then in that case, I want that alpha and beta should be two diagrams which are equivalent, actually isomorphic in the technical sense of the word, okay? And now it turns out that this definition of intrinsic equivalence, which has this strange, very big existential quantifier, because it says there exists such a P. So this is the definition containing this unrestricted existential, very abstract quantifier. This notion is, neked nem szabad szólni, okay? Jézus Mária. There were some disturbances here, I'm sorry. But this is equivalent to the ordinary notion of equivalence. So for instance, if C is a category, if C is a category and I consider it as a L subcat structure, then two objects of the category are equivalent, intrinsically equivalent, if and only if in the category as a structure, I'm sorry, there is some disturbance here now. So that they are intrinsically equivalent in the structure, if and only if they are isomorphic in the category of C. I made a precise statement and this statement actually can be verified by hand. So if you now sit down and look at the definitions, you will see by a little experimentation, a little play, that what this is, what I wrote down is true. And I'm now saying that there is a lot more that is true. That if X is a graph or even a category sketch with some triangles in the graph marked commutative, etc., then these two diagrams, alpha and beta, are intrinsically equivalent in M of C if they are isomorphic as objects of the diagram category C to the X. So this is an example of how the intrinsic equivalence works. Now, for any signature L, I'm now repeating something that if I completely generally, I have that two X objects, alpha and beta, are intrinsically equivalent, then automatically, and this actually doesn't use the extending the identity part of the definition, then they are actually satisfying the same false properties. Now, when we go to the example of the abstract set, this very intuitive example, slightly different from the category example, then when I have that this L structure is a model of a kind of minimal theory of abstract sets, which it is found by a slight experimentation, and in my paper on the abstract set theory, I give it explicitly. Now, just omit these two lines here, okay? So then once again, if I consider this model of minimal set theory, then they are isomorphic in a sense which is completely analogous and equally simple as the notion of isomorphism between two diagrams for the case of categories. Now I have that if the simple notion of isomorphism in a model of set theory in the abstract set context will be such that every property, simply absolutely every property that you can write down in the language which comes with faults, I cannot show the stupid. I'm sorry. I cannot show the key. I don't know what's going on. Sorry. No, I am sorry. This doesn't. Oh God! Again, this thing doesn't want to go away. This line.
I think if you don't move the mouse for a couple of seconds, it disappears.
All right. Yes. Well, abstract set theory is Bourbachian. Now, this is the line here, and let me, okay, just for the sake of emphasis, let me go to the pages where I make a sort of formal definition of what it means for a theory to be Bourbachian. So let me, okay. This part of the slide is about abstract set theory. Now here it is, okay? A global umbrella theory of structures, such as Bourbachi's set theory, okay? Set theory as they produce in great detail, in a complete formalism, they They actually present it in their book, which I think in 1968, and it actually originates in French versions already existing in from the 1930s. Okay, so an umbrella theory is Bourbachian, and I'm introducing a new word. If all its definable theoretical predicates, P of A0, A1, etc., referring to structures A0, A1, etc., of respective species, S1, S2, etc., are invariant. All such predicates are invariant under the identities S equality sub S1 and equality S2, which are appropriate for the species S1, S2. It is the quasi-formal description of A0 is so identical to B0, etc. And the P predicate holds for the A's. What happened? Sorry, I don't know what happened. Okay. I don't know what's this. Sorry. Then I click for no. Then it goes back. Okay, so here is this simple invariance property. But now realize the whole point, there is a universal quantifier on the P's. So Bourbachi's own set theory is not Bourbachian. And Lavir's first order theory of the category of sets is not Bourbachian. If isomorphism, as would be natural, is the adopted notion of identity for the usual species of structures like groups, topological spaces, etc. The reason is this, a very simple one, which actually appears in Bourbachi's book itself. Consider the species of structures of bare sets, both as S1 and S0 and S1. This is, or in abstract set theory, these are called sets, but in the category context, they are objects of a category. Now, the language of the umbrella theory allows the predicate P, which is the usual equality or Frege equality in the usual first order theory of a universe of sets, and also in the first order theory of a category. You see, in the first order theory of category, you want to, for instance, to say that take two arrows and now assume that they are composable. And now you put this condition that they are composable. It means that the codomain of one is equal to the domain of the other. You use an equality of sets or objects in this case, okay? So equality is in there in the umbrella theory. But of course, invariance fails in the most obvious way. Just because two sets are equivalent, the 0 sets and the 1 sets, and the first on the left ones are equal, it doesn't follow that the right ones are equal. Now, abstract set theory, on the other hand, is Bourbachian in the new sense. Okay, of course, this means, for instance, that I cannot say this is one of the main and most obvious things that I cannot say as a proposition. I cannot use as a grammatically correct proposition referring to two variable objects that they are, or variable sets that they are the same, they are equal. I cannot say that. This is part. But of course, to specify, it's not enough to to exclude certain things, but you have to define completely the grammatically correct language, okay, in a positive manner, not by exclusion or a series of exclusions. Now, internal topo theory becomes Bourbachian if the category theory of the false language over L sub cat is adopted, but not without such a move. Okay, so now I'm going to, let me just see where I am at the moment. It would be now nice to look at the three examples in some detail, namely L sub cat, L sub, so the abstract sets, and also the ANA functors. And what would be nice, and as a kind of introduction to the mathematics of faults over them, is that we start with ordinary objects like a category, and by a canonical construction, we make them into structures of the corresponding signature. The same thing in the case of abstract set theory. In fact, any model of set theory can be now made, recoded as a structure of the corresponding structure over the corresponding false signature. And the point about this thing is that now one sees that certain properties or constructions in the category can now be expressed in the for the corresponding L structure. And the fact that now this new way of doing it in the L of the false signature is the same as the original one is not a precise, exact statement, because you are going to say that the category satisfies such and such if and only if M of C, which is the corresponding structure, satisfies such and such. So it becomes a real translation in this sense. It's not just an analogy, but a rigorous statement of equivalence of meanings. Okay. Now, so this carries. This is done, and certain mathematical things are done for those three examples. But I'm going to skip all of that and let me go to a very general statement of faults. Now, this is, I call it the Lindström context. You will see why, but it's not important at the moment. An important restriction here is that this is false only when you model faults in the category of sets. And as a matter of fact, it's very important that just like in any kind of categorical logic, that you should be able to model a theory, for instance, in almost any category. And the minimal conditions, for instance, in a topos, for instance, that has already a lot of structure, but even much less should be possible. So this is a restriction. So therefore, I'm not looking at faults only in the set valued case, but then I is sort of expanding the original concern about the syntax of ordinary first order logic in faults. I expand that. Okay. So the Lindström context for faults is obtained from the classical Lindström context for ordinary first-order logic by replacing isomorphism by false equivalence. This almost completely defines what I'm going to do. The possibility of doing this is the first main fact. The new context, there is something missing here. So I'm sorry, there is something that I don't understand exactly this sentence, but I think it doesn't really matter. The new context serves as a framework for a natural generalization of faults, for faults of Lindström classical theorem, which at the end of this set of notes is actually stated in a rigorous manner. Now I say something about what Lindström theorem does, but I'm going to skip it, okay? Because actually the context is more important than the theorem itself. Now, the terminology. Now, here's a very important thing, that I consider all false signatures at the same time, okay? So here I repeat the definition of augmented structure, which I'm not going to repeat it. It's right here, okay? This is for a given L. And here is the first main move. So an LX class phi. So phi is a class of X-type augmented L structures. It's just any class at the moment, all right? This class is given by, it's a subclass of all augmented structures of this type. Now, this is invariant. If it is invariant I call it invariant, it is closed under L equivalence in the obvious sense. It's right here, okay? Now, let me just say this. Suppose that phi x is a false formula over L with a free variable x. X is the set of objects of the category of elements for a finite functor x. So x vector is the really same thing as the capital X. This is part of the basic syntax of faults way before any quantification or anything happens. Now, so a typical or quasi basic type of invariant class is when I take the model, the category of, the class of models of this formula phi x, okay? Here I say this in some detail, okay? This very simple thing. Now, the soundness of false equivalence becomes the statement that phi obtained from any little phi is an invariant class. Now, we organize all invariant classes into a simple-minded, super large, I believe in universes, discrete vibration L over a category L sub 0 of augmented signatures. You will see that something very simple is going to happen. But before that, let me just stop and say that obviously there are many more invariant classes than the ones I gave. Why? Because there are huge extensions of first order logic which are model theoretical, even model theoretical in the false sense. For instance, there is an obvious infinitary logic over faults and even second order logic. again, it automatically will give rise to invariant classes. And so this is how we expand the original context. And this expansion will give rise to intelligent questions and intelligent answers to those questions. Now, I say some words here that this is a Laberian hyper doctrine with a familiar logical operations, just to connect it to familiar notions. And these operations, in fact, include infinitarian second order ones given as adjoints. So because there are so many more classes, as a matter of fact, than invariant classes than just ordinary first order ones. So I'm not going to spell out the full structure of this vibration, only the part that is relevant to the finitary first order logics with dependent sorts. In fact, the full structure is revealed only when the base category L0 is also enlarged. But now I have to define the base category, okay? The L sub 0 is the category of augmented signatures. A very simple idea is here. Suppose you have two L signatures, L sub 0 and L sub 0 is part of L. Now, this is a legitimate arrow in this big category if this embedding is initial, and here is a definition. But don't worry about it. It means that the L0 is downward closed in L. And the typical example would be, unfortunately, I didn't bring this up, that when you take the AMA functor signature, then this talks about functors which are free living. So there are two categories and the functor between them. And therefore, the L sub cat signature has actually two initial embeddings into that. So but this roughly means that when you say anything in L cat, but inside the L AMA functors, then this is the same thing as if you talked about that category in L sub cat. Because all references that you possibly can in L sub AMA fun is already there in L sub cat. Okay, so the objects of L sub 0 are these augmented signatures, and the morphisms are null. So here I have to talk about morphisms of augmented signatures as it is shown here. And here it means the requirement is that actually this extension F also just simply extends the origin x0 to x in this manner, okay? Think of psi as a substitution of variables. If you really want to get clear about this hyper-doctrinal view, okay? Now, it's very obvious that this is a category. It's an associative unitary composition that we have. And this fact doesn't use anything. Now, these underlined versions of the letter L are going to be used as general notation for augmented signatures. And I simply, just to have a notation, the capital L or big L of L underlined is the collection of all invariant structure. So now it's very important that not only that the classes are big, but actually now I look at collections of classes. But it's not bad at all. This is a collect. So capital phi is basically just stands for a formula of some kind, right? So so therefore this script L of L underline should be thought of the set of all L formulas with the free variables x, but formulas in a very general sense of the word. But you don't have to think of that because this definition is awfully, completely explicit and rigorous, okay? I only look at invariant classes, of course. So now, here is the most important idea. It is that that this is a functor. Now, what does this really mean? It means that suppose, so I'm going to explain this, but and the first I use some definitions and notations on a lower level. So suppose you have an augmented structures M and alpha, okay. This is a wrong, unfortunately, this is a very wrong notation here. It's a big mistake, actually. It's not a class, but it is an L structure. So sorry about that. This is bad. This thing is bad. Okay. Erase it. I don't know why I wrote that. Now, go back to this. So we have these two languages, L0 and L, and the reduct of M is the simple notion. You simply reduce M to F. Is the augmented structure which is now over only in L0, when categorically the signature, the reduct is simply a composition of functors. Okay, and there is a similar simple definition of what are reduce and augmentation. Here there is also a diagram which shows in a sort of comprehensive manner what's going on. And now comes the definition. Suppose now I have now a class, and this is the correct notation, and an L0 class, and I have legitimate embedding and initial embedding of the smaller language into the bigger one. Now the co-reduct of phi, even by this extremely simple definition, M is in the co-reduct, so M is of the bigger type, M underlined, and this is going to be in the co-reduct if and only, of course, when the reduct is in the original class. And now comes an elementary but essential observation, but one that's sensitively dependent on the initiality of F and the very definition of false signatures, that co-reduction preserves invariance. But when you think of isomorphism, then we are saying something extremely trivial thing here. Something like when you consider, take a ring, then it has, say, an underlying additive group. Then the additive group is a reduct of the original ring. Now, if two rings are isomorphic, then of course the corresponding additive groups are also isomorphic by an isomorphism which is a reduction, a reduct of the original isomorphism. And this is what we are saying now in the false context. But this requires a bit of inspection. And in fact, for instance, the initiality of the expansion of the L0 to L is essential in this. So this is now the main operation on classes, and this is what makes this into a functor, or if you wish, a discrete up vibration. Now let me see where I am here. I think I am more or less at the end of my tether, so to speak. All right, and now I need some instruction for what is going to happen. Do I hear what you say? I don't hear.
Yes. So sorry. You mean you finished, or you
no?
Because
No, wait a minute. No. You have to tell me.
Yeah. So
no, you have to tell me what I should be doing.
So from the point of view of the schedule, I would say that if you need 5 minutes, you can take them, but not more than 5.
Look, in a sense, I need a lot more than that. There is no point actually stretching this away. Okay, so
okay, then I would say that
maybe just a few sentences. That after this basic construction here, one introduces the logical operations, and then then I have a context which contains at the moment as a part what contains the soundness of L equivalence for the syntax, because the syntax is suppressed into the logical operations on these classes. But we can now do much more of it, because now I can take an arbitrary class and put some conditions on it. Namely, what I'm going to try to do exactly as Lindström was doing, that suppose I take an arbitrary invariant class and I ask whether it generates a logic which is like first order logic, at least in the model theoretic sense. And believe it or not, the answer is that it can do that only when the original class was already in false in the first or ordinary first order logic over false. And this is an extension of Lindström's original theorem, which was very celebrated at the time when it came out. Thank you. I'm finished.
Okay, thank you for Professor Makkai. So we must have a silent applause, because this is what Zoom offers us. Some people are doing an applause, but I'm not sure you can see it. So now we have the question time, and so I thank all the people that have joined us. And now, if you want to ask a question, just mute your mic and you can speak, and if Professor Makkai will reply. So again, thank you, Professor Makkai. And now, if someone wants to speak, I think you should be able to unmute yourself and speak.
Maybe I can ask a question. Mihai, this is Phil Scott.
Yes, I recognize you. Hello.
Hi. Can you mention a little bit about, since you've discussed so much the soundness theorems, what roughly do the completeness theorems look like?
It is stated in my abstract, by the way, and I don't think I can. No, this is not. I'm going to say it again. But I cannot say it more kind of comprehensively than it was stated in the abstract. And it is the following simple thing. Imagine that you have an L signature, for instance, L sub cat, okay, 4 categories. Now, in this L sub cat can serve as a simple multi-sorted signature for ordinary first order logic with equality. in which there are 5 sorts, and all those arrows operate as unary operation symbols. And this gives rise to a ordinary first order logic. Now, the folds formulas is really a proper subset of this set of all formulas in the ordinary logical sense. And now here is the theorem. If you have, say, a sentence in this in the ordinary logic over L sub cat, and suppose that this sentence is invariant, now let's say under ordinary category equivalence. Okay, this is a supposition which now doesn't require any new notion. Then, and now this is the statement, then this formula is going to be logically equivalent to a false formula. This is the completeness. So this means that L equivalence is sort of complete in the sense of there is no more than L equivalence for the false language. There is a better and more useful way of saying this, and this completeness statement is actually, it's very interesting that actually in its form, in its structure, goes back to the Craig interpolation theorem. But I cannot simply say that it's a generalization of the Craig interpolation theorem. That would be too much to say. But the structure and the proof of it is quite similar.
Thank you.
Someone has other questions?
By the way, let me, okay, am I interrupting? Let me just say that I'm quite ready to answer questions later on when you have had time to look at the slides and etc. So don't hesitate to contact me about anything that you would like to ask or know.
Maybe one. Sorry, who's speaking?
Mirna is speaking. Hello. Well,
Hi.
maybe I missed something during the talk, and I will certainly look into your slides as you just suggested. Very good idea. But I want to ask you why you were looking at the Bourbakian set theory and not ZFC in that. Is ZFC set theory Bourbakian? You know, you had the slide where you said the Bourbakian onset theory is not Bourbakian. So is ZFC Bourbakian?
No, I just explicitly said that it is not Bourbakian. And I even gave a detailed argument for it.
Was that at the beginning? Because I joined.
No, it's not at the beginning. I even was reading. Okay, let me try to bring it up. I hope you don't mind.
Sorry, I got lost. No, just to the context.
I bring it up, all right? So let me just see that it's number 4, sorry. So let me quickly go through this, okay? When I say that some set theory, for instance, Bourbaki's set theory, by the way, is really quite equivalent to ZFC. It has very strange elements. It uses the Hilbert epsilon symbol and whatever, but it doesn't really
for
matter.
the
It is
observable choice, yes.
correct. So the choice is actually built into the logic. It's very strange, but when it comes down to the use of it, it is quite equivalent to ZFC. So you can take ZFC quite simply as it is now. So I say that such a thing would be Bourbachian, right? If now briefly put, everything that you can say it in, this P is now, there is a universal quantifier on it. If all definable P's are invariant under isomorphism, okay? I don't know why
I think you want to share the slides. We don't see them.
Yes, Professor Makkai, you're not sharing. You forgot
really?
You forgot to click on share screen. Yes.
Yeah, okay, sorry. No. And I lost. No, it's here. Yes. Okay, so let me go back here. Yeah. So once again, a would-be Bourbachian set theory would have the property that anything that you can say in it, this P's would be such a thing. If anything that you can say would be invariant under isomorphism. Here is the formal way of saying it, okay? Now, Bourbachi's own set theory and ZFC, these are not Bourbachian. And here is the argument.
By the same proof, that's what you are saying. ZFC has the same proof as Bourbachian. Is that what you are saying? Because here you are only talking about Bourbachi's set theory.
I'm sorry, I repeated. I don't know.
Well, so you showed here by this argument that Bourbachi's own set theory is not Bourbachian.
Yes.
And
correct.
are you saying that ZFC by the same proof is not Bourbachian either?
Yes.
Okay, so that's what I missed in your talk. Yes, thank you.
I'm sorry. Okay, so that's it.
No, I understood. Thank you very much.
Sure.
So while people decide if they have other questions, maybe I will say something. So we already have recorded another version of this talk, more or less on Friday, and the other version is a little bit less condensed. So because it doesn't talk about Lindstrom theorem, so there is more space for the first definitions. So if Professor Makkai agree with it, I will put both of them on YouTube so that people can see both of the versions.
Yes, I agree to any such thing. Also, all the slides that I submitted.
Of course, the slides
are open to anybody who wants them. Okay.
So just for the audience that is interested, so on the web page there are already the slides of the talk, and then I will upload two versions of the video. The second one will be more condensed and it contains more material and the questions, of course. And the first one is a little bit more relaxed, and so the first definitions are a little bit less dense in the other version. So now back to questions, if someone has another question. Otherwise, we thank the speaker again and we call it a day.
But I'd like to make just one or two remarks, all right?
Please.
And it's just the fact that this false is a very old thing, okay? So it is 25 years old, all right? And in a sense, it hasn't been really treated very much in the literature. And I haven't even made any hint of what I consider my main use or uses of it, okay? So on the one hand, there is a lot more, or maybe not a lot, but at least some more. But also, these things are sort of in a limbo. It's certainly not in officially published literature. If you go to my website, for instance, then you find more, okay? So that's it. Thank you.
Thank you. And I think if there are no more questions, we can call it a day. It seems that there are no more questions. So I would like to thank the speaker again and thank everybody that has joined. We had a quite big public audience also today. And so I thank also all the committees of all the members of the scientific committee. And I would say, see all of you next week with Benno van den Berg. And you can find the title of his talk on the webpage. And again, thank you, Professor Makkai, and see you, everybody. Goodbye. Okay, I will stop the recording.